Okay, so let's start. Today I'll solve two questions from functional analysis. This is a question number 43 and question number 16 from Gate 2022. So I'll play the video first, question number 43. Okay, so today I'll solve Gate 2022 question. This is a question from functional analysis. What it is saying? So this is question number 43. Given that x, y and z are Banach spaces and T is a linear map from x to y and S is a linear map from y to z, and what else is given? That S is bounded and injective also given. And in addition, if S compose T, which will be map from x to z, is bounded is given, then which of the following statement is true? You have to check. Four options are given. That T is surjective, bounded or not bounded. You have to check which one is correct. Okay, we'll solve this one. So in order to solve this is the NPTEL reference. This you can check for references. Okay, so let's try to solve this question. So given T from x to y is linear. Before that, all are given the Banach spaces. X, y, z are Banach spaces. Means complete non-linear spaces. And what is given? T from x to y is linear. S from y to z is linear, bounded and injective. And in addition also given, so these are given. S compose T, which is a map from x to z. So this is linear and bounded, right? So these are given. So using all these three, we'll prove that T must be bounded. So claim. So we'll prove this one, that T will be bounded. T is bounded. Okay, and for linear operator, bounded, what is so? I is so we have to show that norm Tx is less than C times norm x for all x in x, capital X, right? So this is mean the boundedness for a linear operator, and also this will imply that T is also continuous. So for linear operator, continuous and boundedness are the same thing. So how we will prove this, that T is bounded? So for this we will use one result. So there are different techniques to showing that an operator is bounded. So here one technique is, we'll show that closed graph theorem. We will use this one. So let me write the result. Theorem. This is called closed graph theorem. So let T is a linear operator from x to suppose y, be linear. Then the following are equivalent. First of all, T is bounded. Second one, the graph of T is closed. Means what is graph of T? This is x comma tx such that x belongs to x. So this is a subset of x comma cross y, right? The graph of T is closed in x cross y, right? And third, so and also means T is closed. So whenever we say that T is closed, means the graph of T is closed. So this is same as saying that T is closed. And 3, so it is saying that if xn tends to x and txn tends to y, so this is in x, in y, and this is in y, right? Then T of x equals to y. Means if xn converges to y, then T of xn must converge to T of x. Right? So these three are equivalent. So and xy are Banach spaces. Let me write it here. So here xy are Banach spaces. So in Banach spaces, T is bounded is same as T is closed, mean the graph of T is closed. And if xn converges to x in x and txn converges to y in y, then T of x equals to y. Okay, so we'll use this theorem to prove that T is bounded. Basically, we will show that using this, we will show that T is bounded, right? So we'll use this theorem. Okay, so here what is given? So in order to show T is bounded, we need to show. So here, in order to show T is bounded, we need to show we need to prove if xn is a sequence in x such that xn tends to x in x and txn converges to y, then so assume this one, then T of x equals to y. So So right, so this we have to prove. Then T will be closed. So then T will be bounded. We are done. So assume this one. Assume xn converges to x in x and txn converges to y. To prove t of x equals to y. Now what is given? It is given that S compose T is a linear and bounded, right? So now given that S compose T is bounded. So here bounded means continuous, right? As xn, and this S compose T is a map from x to z. As xn converges to x in x, so by the continuity S compose T of xn converges to S compose T of x, right? So this is just the continuity, means here S compose T is bounded, so it is continuous. So S compose T of xn will converge to S compose T of x. And again, what is given? That S is also bounded, means S is also continuous. So we will again now use this one, right? So txn converges to y. So this is also given. S is bounded as txn converges to y in y, and S is a map from y to z. So S of T of xn converges to S of y, right? And these are in z, right? In z. Now you know that as we know S compose T of xn is same as S of T of xn, right? So because these are the left hand side, both are the same, and both converges to here, this converges to here and this converges to here. So by the uniqueness of the limit, what we will get? That S compose T of x should be equal to S of y, right? Because this converges to here and this converges to here, so the limit must be same. So this we will get. Now what is also given? What is also extra given? That S is injective. Now we'll use this fact that S is injective. So as S is injective, so therefore if it is injective, then T of x equals to y, right? Because injective means if suppose some operator T is injective, means T of x equals to T of y implies x equals to y. So Tx equals to Ty. So you have got this. So this is we need to prove, right? This is our claim. So we got Tx equals to y. So therefore by closed graph theorem, so which implies T is closed, which implies T is bounded by closed graph theorem. So we have shown that T is bounded, right? So therefore what we have got here, the T is bounded but not continuous. But for linear operator, continuous and bounded are the same. So this is not. So T is bounded. If T is bounded, so T is not unbounded. So only remain to check the option A. So let's check option A. So it is saying that T is surjective. Right. So this is bounded implies that T is continuous. Because these are linear operators. So now you have to check that T is surjective or not. So we'll show that T may not be surjective if this condition is given. So it means there is linear map which is not surjective but it still satisfies this condition. So we'll give an example of that. Now we'll show that. So now we will show T may not be surjective. Right. So we will give an example. So let's take, so define this T from, so L to N. So this is a square summable sequence from L to N. So these are basically Hilbert spaces, so Banach spaces. So how we will map? So this has a basis. These are Sauder basis. I am mapping En to 1 by n En, right? And now I am extending this to linearly to all x. So means how I am extending for x in L to n. This you can write because these are Ens are orthonormal basis. One can write x equals to x inner product En and En, right? So now we will extend it linearly. So T of x will be summation over n x inner product En T En, and what is T En? So this is n summation x inner product En. This is 1 by n En, right? So let me write it here, 1 by n En. So basically, so this is our definition of T. Now check, note that T is bounded. So what is T of x? So you have to calculate the L2 norm of this, right? So you are calculating the L2 norm of this. So using the orthogonality, what we will got? So Ens are orthonormal basis. So basically what we will got, 1 by n square x En. So why this is true? As Ens are orthonormal. Right. Now, so what we will next do? So use the Cauchy-Schwarz in the numerator. So this, if you use the Cauchy-Schwarz, so what you will got? So this you will got basically norm of x square and norm En square by Cauchy-Schwarz. So this is saying that this inner product is less than this one. So now Ens are all have the orthonormal, so these are norm 1, so this is basically less than n 1 by n square. Let me write it here, because x is n independent, so this is norm x square and Ens are norm 1. Right, so and this is summable 1 by n square, so it will be c times norm x square. So which implies that T is bounded. right? Now we will show that T is injective. So for injectivity you have to show that T of x equals this. So these are linear operator. If Tx equals to 0, you have to show that kernel is the only the zero vector is there, right? So if T of x equals to 0, which implies summation 1 by n x en is 0. So this is overall n. And this is 0 means what? So this is 0 vector, which implies, so x en should be 0 for all n. And this is the ens are orthonormal basis. So x is orthonormal to all the bases, orthonormal basis, right? So which implies x should be the 0 vector. So this is one result, that if x is orthonormal to all the basis elements, then x must be 0. So x is 0. So kernel of T is only the 0 vector. So which implies, so T is injective. So you have got that T is bounded, T is injective, and obviously T is linear. But T is not surjective. Claim T is not surjective. T is not surjective. This you can also show other way, but I am giving an one, that there exists a vector in the L2 which is not in the domain. So let's take y to be this vector, summation over n 1 by n en. So note that this is in L2. If you take the L2 norm, means take the square sample, then this will be finite. Now we will show y does not belongs to range of T. It means, so this implies that T is not surjective, right? So if so, then there exists x belongs to L to n such that T of x equals to y, or so this means 1 by n x en should be summation 1 by n en, right? So this is the meaning of this. So now so these are both sides are the same, ens are the so orthonormal basis, the corresponding coefficients should be same. So which implies, so 1 by n, so therefore because T is injective, means ens are orthonormal basis, so you subtract, what you will get, that x inner product en is 1 for all n. Right? But this can't be, this is not possible, as x is in L2, which implies x, what is x? Right, x we have written this, x inner product en. So what is L2 norm of x? So if you write down L2 norm, because of the orthogonality, you will get this. And which is finite because x is a single vector. So as the series is finite, which implies x en should be goes to 0. Right? But what we have got? But as we get x en is 1 for all n, so this is a contradiction. So what contradiction to what? So we have assumed that t is surjective, right? So which implies t is not surjective. So which implies therefore t is not surjective. Means there does not exist any x such that t of x equals to y. So t is not surjective. Now, so we have got that t is not surjective. Now we have to, what else remains we have to check? So take s equals to t, and t is this linear vector, this t. This t we are taking. So what are the assumptions we have to check? That t is a linear, s is a linear bounded injective, then s composed t is bounded. So you have, so that this t is not, if it is not surjective, it can still satisfies all the assumptions. Right? So let's check. So you have taken s and t both to be the t. T as the above example. Then t is linear, bounded, injective, and s composed t. What is s composed t? So this is basically t square. So how it will be t square? It will be mapped from again L2 of n to L2 of n. So it will be basically map en to 1 by n square en. Again, as we have checked that t is bounded, again one can check similar to t, that t square is bounded. So you have shown that for s is a linear, t is linear bounded injective, and s composed t, which is t square, is again bounded. But s, which is t, is not surjective. Or t is not surjective. Sorry, t is not surjective. So if t is not surjective, still all the things are satisfied. So therefore, it is not necessary that t has to be surjective. So therefore, which options we have got? That t surjectivity is not necessarily true. This may not always be true. T is bounded but not continuous. This is not true because bounded and continuity are the same for linear operator. T is bounded. This is true because we have got t is bounded. T is not bounded. This is also false. So option C is the correct option. Okay. Okay, so question number 43 is done. Now we'll move to the next one, question number 16. Okay, so today we'll solve Gate 2022 question. This is a question from functional analysis. It is a question number 16. So it is saying that let Ek be an orthonormal basis for the Hilbert space H and define Fk via this Ek plus 1 and Gj is summation n equals to 1 to j minus 1 to the power n plus 1 En. Then you have to compute this series summation k equals to 1 to infinity mod Gj inner product Fk square mod square. So 4 options are given. You have to check which one is correct. Okay. So in order to solve this is the NPTEL reference. This you can check for the references. Okay. So let's try to solve this one. So we have to find this series. Okay, so what is given? Fk and Gj. Ek for k belongs to n is an orthonormal basis for H. Right, and Fk, what is Fk? Fk is defined to be Ek plus Ek plus 1 for k belongs to natural number. And how Gj is defined? Sum n equals to 1 to j minus 1 to the power n plus 1 En, right? So Fk and Gj are defined. I have to find the inner product Gj with Fk first. Then we have to find the sum. So what will be this? We have to find Gj inner product Fk. So let's find this one. So what is this? Gj is basically this sum. N equals to 1 to j minus 1 to the power n plus 1 En, and Fk is Ek plus 1. Right. So note that Ek's are orthonormal basis. So for k not equals to some k dash, they are 0. And if this becomes same, then their inner product will be 1. So use this one, right? So what we will get? So suppose j less than k, strictly less than k. Then in this sum, all the term is less than k, right? So if you take the inner product with this one, you will get 0. Because this is k and k plus 1. So for this, you will get 0 if j is strictly less than k. Now what happens if j is k? So this case, if j is k, so there is then one sum Ek will be there, and this is inner product. If you take Ek, so you will, this inner product will be 1, and so you will get this sum, right? So for j equals to k, you will get this only one term minus 1 to the power k plus 1. So when j equals to k, only that inner product will be non-zero. Otherwise, all the inner product will be 0. And what happens if j is bigger than k plus 1? If j is bigger than k plus 1, so suppose, so there are, so because here it is only 2 terms, so only 2 terms here will matter, k and k plus 1. All the other inner product will be 0. So k and k plus will be there, certainly because j is bigger than k plus 1. So therefore, whenever Ek and Ek will be there, it will get 1. So you will get this coefficient minus 1 to the power k plus 1. And whenever Ek and Ek plus 1 will take the inner product, you will get minus 1 to the power k plus 2. Right, so these 3 possibilities are there. And now look at this, whatever, suppose this k is even or odd. So if this is even, then this will be odd, and if this is odd, then this will be even. So one thing will be plus and one thing will be negative. So what you will got basically? So this is 0 for j strictly less than k. This is minus 1 to the power k plus 1 if j equals to k, and this is again 0 if j bigger than k. Right, because one thing will be even, one thing will be odd, so one will be plus 1, one will be minus 1. So this you will get the inner product. Now we have to find this, right, this series. So what will be this series? So then summation k equals to 1 to infinity, right? K equals to 1 to infinity gj of k. gj fk. So if k is bigger than j, then so let's break it into 3. So sum so first sum when k is j minus right. So this is so k equals to first 1 to j minus 1. This sum first gj fk plus the next when, so this is only the jth term will be there, so it is gj comma fj, right, and the last when k is bigger than j, so k equals to j plus 1 to infinity. So note that this term will, this is same as k is less than j minus 1 plus what is this term? So gj fk when k equals to j, basically this is, so let me write it first. Plus this sum is basically k is bigger than j, right? Now what is this? So first one for j k less than j minus 1, this is 0, so the first term is 0. Second term corresponding to the k equals to j case, so this is minus 1 to the power k plus 1. So this is minus 1 to the power, here will be j plus 1 square plus this term again for the k bigger than this case, so this is again 0, so this will get 0. So what will be the sum then? So this is minus 1 to the power, so it will be plus 1, so the sum will be 1. So this series sum will be 1. So what we have got? So which option is correct then? So 0, which is not true, j square, this is also not true, this, so the sum will be 1. So option D is the correct one. Okay, so okay, so we have also solved question number 16. So today we solved both the questions from functional analysis, question number 43 and question number 16. Next week we will again solve two questions from real analysis. Okay, then let's stop for today. We'll meet again in the next week.